Kusumita. I am Assistant Professor of Chemistry in BSH. So, today's topic is spectroscopy. We have already started spectroscopy. We have completed UV spectroscopy, rotational and vibrational spectroscopy. Today we will learn about another spectroscopy step. Okay. So, first one is IR spectroscopy. IR spectroscopy means infrared spectroscopy. So in IR spectroscopy, what happens? The incident radiation is microwave radiation. Sorry, infrared radiation. Incident radiation is infrared radiation. Okay. This is infrared radiation. Now what happens? Infrared radiation is basically thermal energy. Now if we are giving some infrared radiation to a matter, what happens? It is basically thermal energy, so it will absorb some amount of energy, and due to that absorption, some vibrations will be taking place inside the molecule. Okay, some vibration. These vibration are basically two types, and the first one is stretching vibration. Okay, first one is stretching. Stretching means it will stretch along the bond length of a diatomic molecule. Let's say this is M1 or M2. So, if this bond is basically elongated and compressed, then this is known as stretching. Okay, stretching vibration, and another one is bending vibration. Another one is bending vibration. In bending, what happens? Let's say this is a water molecule. So these two bonds will be bending upon like this. Okay. So these two bonds will be like this. So this is bending vibration. Now this infrared radiation is basically shown in the form of transmittance. Okay, in the form of transmittance, and the wavelength region that it is involved is 600 to 4000 centimeter inverse. Now in between this region, 6000 to 1400 centimeter inverse is known as molecular fingerprint region. Molecular fingerprint region. Okay. So from the concept of the IR spectroscopy, we can assume that if the molecule is highly polar, then it will show us strong IR bonds. Like if we give an example of CO, CO bond is polar bond, so it will show us strong IR peaks. Okay, now if we compare this with CN, let's say, with CN. So CN is less polar compared to CO, so it will give comparatively weak bond. Okay. Comparatively weak, or we can say moderate IR peaks. This is comparatively weak. Okay, so that's how we can determine the IR spectroscopy. Now, whenever we are given any unknown molecule, first we run through a IR spectrometer, then the peak that we are getting, we have to match that peak with our database. So from this database, we should know that what the molecule, the vibrations, and what are the groups that are present in our unknown sample. Okay. Now, next spectroscopy is NMR spectroscopy. NMR means it's nuclear magnetic resonance. Okay. So the name itself suggests that this spectroscopy involves some intrinsic nuclear magnetic moment. Okay. Now the principle of NMR spectroscopy is that the intrinsic magnetic moment is in play with the external magnetic field. Okay, and this interaction that we are getting that's how we will get the peaks in NMR spectrometer. In NMR spectrometer, we identify the NMR spectrometer as the field, the strength of the external magnetic field, like 200 megahertz, 600 megahertz, etc. So these are the strength of the NMR spectrometer. Okay. Now in NMR spectroscopy, what happens? If the number of proton and neutron within a nucleus are equal, then that atom will not show any kind of NMR signal. That atom will be NMR inactive. NMR inactive. But if the number of neutrons and protons are different, in case of any atom, neutrons and protons are different in case of any atoms, then we can get the NMR signal, and that atoms is known as NMR active atoms. Okay, so let's say for example carbon 13 and carbon 12. In case of carbon 12, the number of neutrons and proton is 6. Number of neutron and proton are equal. That is why carbon 12 is NMR inactive. It is NMR inactive. Okay. And this in case of carbon 13, neutron is 7 and proton is 6. So the number of proton and neutron is different. That is why carbon 13 is NMR active nucleus. Here. Now we are getting to an important concept that is shielding. Shielding effect in NMR spectroscopy. Shielding effect and de-shielding effect. Now if there is a nucleus, okay, and if the number of electrons in the outermost shell is higher, that means it is shielding the nucleus. If the number of electrons is higher, then this nucleus will feel comparatively lesser of the external magnetic field. That means the nucleus will less feel the external magnetic field. Okay, the feeling of the nucleus will be less. So external magnetic field will have a lower amount of impact on nucleus. Okay, so number of electrons, if it is higher, then the effect of B0 will be lower on nucleus. Okay, so this particular nucleus will require low amount of energy to resonance with the external magnetic field, and it will show a lower ppm value. Okay, lower ppm value, or we can say chemical shift value. Chemical shift value. Okay. Now this whole phenomena is known as shielding effect, and de-shielding effect is just opposite to this phenomenon. De-shielding effect. What will happen? If the number of electrons are comparatively less, then the external magnetic field has a heavy impact on the nucleus. So there will be a strong interaction between the intrinsic magnetic moment and the external magnetic moment. Okay. So if the effect of B0 is high, then it will be requiring higher amount of energy to resonance with the external magnetic field. So it will show the signal at a higher ppm value. Okay, it will show a signal at a higher ppm value. So this was all about shielding effect and de-shielding effect. Most studied NMR are proton NMR, 1H NMR, and carbon 13 NMR. These two NMRs are the most studied NMR. Now, if we want to find that in case of proton NMR, how many signals will appear in case of carbon NMR, the number of signal that is based on the chemical environment, proton and carbon are decided. Okay. Now, for example, CH3, CH2, let's say CH3, CH2, Br. Okay. Now here, if we want to find the proton NMR signal, the number of proton NMR signal in that molecule, so what will happen? Here, the number of protons are 2. Here, the number of protons are 2, and here the number of protons are 3. Right? So 3. Here the number of protons are 2, and here the number of protons are 3. But due to the presence of this bromine has minus I effect. So what it will do? It will pull the electron cloud to itself. So this HA and HA, these 2 protons will give 1 signal, and these 3 protons, which is connected to this carbon atom, let's say this is C1 and this is C2. In case of C1, 2 hydrogen atom will give 1 signal, and in case of C2, 3 hydrogen atom will give another signal. So in this particular molecule, the number of signals proton NMR will be 2, because there are two chemically different types of hydrogen atoms are present in this molecule. Okay, so that's how you will find the number of signals in case of proton NMR, and if it is carbon NMR, then we have to count the types of carbon. Now in this particular example, if we want to find the carbon NMR signals, then here basically 2 different types of carbon atoms are present. So that is why the number of carbon NMR signal will be 2 in this particular. Okay, so that is all for today. In the next class, we will be covering the next topic. Thank you so much.